It's a love that lasts forever. It's a love that has no past. Don't let me down. Don't let me down.
Welcome, and thank you all for coming. Before we start the discussion this evening, I'd like to acknowledge the land on which the CBC operates. It has been a site of human activity for 15,000 years. This land is the territory of the Huron-Wendat and Petun First Nations, the Seneca, and most recently the Mississaugas of the Credit River. Today, the meeting place of Toronto is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work in their community and on their territory. Welcome, everyone, and thank you for coming to the 2017 CIFAR Massey Talk on Science and Society. I'm Hugh Siegel. I'm head of Massey College, and Massey's history for half a century of building interdisciplinary insight and intergenerational wisdom, part of its core purpose and principle, is part of why we are so honored to partner with CIFAR this evening. 3 years ago, Massey College and the Canadian Institute for Advanced Research came together to inaugurate these talks. We recognize that scholarship and science are powerful tools for understanding and shaping our world, and that it has profound implications for how we live and think. These talks are intended to explore the connections between research and the broader community and to help catalyze new ways of thinking and deeper levels of understanding. Each year, we invite a speaker to examine a subject that is important to the world and that is informed by the rich interplay of ideas between science and culture. Anyone who reads the news knows that breakthroughs in artificial intelligence are coming fast and furious these days. Artificial intelligence promises to revolutionize everything from transportation and healthcare to our relationships with machines and the very idea of what it means to be human. And nothing that happens quickly or is of that kind of importance is without its ethical, social, and economic implications. First, though, it is my distinct pleasure to introduce Dr. Alan Bernstein, a senior fellow at Massey, president and CEO of CIFAR, and this year's laureate for the Friesen Prize for Outstanding Medical Research. Ladies and gentlemen, Dr. Bernstein.
Thank you very much, Hugh, and welcome everyone. I'm truly delighted to be here as president of CIFAR, the Canadian Institute for Advanced Research. I'm very much looking forward to our speaker's talk today from Dr. Joelle Pineau from McGill University. But I'd first like to recognize two CIFAR board members who are in the audience today. Barb Stamietz, our distinguished board chair, and Lawrence Petlin, one of our newest board members. For those of you who are not familiar with CIFAR, we're a Canadian-based global research organization that's sponsored by visionary individuals, corporations, foundations, and the governments of Canada, Quebec, Ontario, Alberta, and British Columbia, as well as partners in Canada, the US, France, Germany, and China. We bring together some of the world's top researchers across disciplines to tackle important questions facing humanity. For example, one of CIFAR's programs, Bio-Inspired Solar Energy, is tackling the challenge of climate change by learning how to harness and store energy from the sun, taking advantage of what Mother Nature has been doing for the last 400 million years, photosynthesis. Others are examining what goes into making a society successful. Some of you may have read about the collision of two neutron stars last week, that was reported last week, that led to the release of gravitational waves. Our fellows in the program in Gravity and the Extreme Universe have played central roles in the recent detection of those gravitational waves from those black holes and neutron stars. And one of CIFAR's great successes, and why we're here tonight, is artificial intelligence, or AI. In 2002, a University of Toronto researcher, Jeff Hinton, Jeff, I don't know if you're in the audience here this evening, brought together a CIFAR program now called Learning in Machines and Brains. Jeff's idea was that we could learn from the original thinking machine, our brains. Jeff pioneered the AI technique now called deep learning, and he is considered universally as the godfather of AI. Last spring, he was recently named a Distinguished Fellow by CIFAR's Board of Directors in recognition of his outstanding science and his long-standing contributions to CIFAR. Jeff's work with other CIFAR fellows, including Jan LeCun of New York University and now head of AI at Facebook, and Joshua Bengio of the Université de Montréal, who are co-directors of our program in Learning in Machines and Brains, have helped to make Canada a true powerhouse in artificial intelligence talent. It's actually hard to pick up a newspaper or turn on the radio without hearing a story about AI these days. And for that, we have Jeff Hinton to blame. Our speaker tonight is another example of Canadian research excellence in artificial intelligence. Dr. Joelle Pineau is a CIFAR Senior Fellow and a leader in the field of artificial intelligence. She's an associate professor and William Dawson Scholar at McGill University, where she co-directs the Reasoning and Learning Lab. Last month, she was also named head of the Montreal Facebook Artificial Intelligence Research Laboratory. Her research focuses on developing new models and algorithms for planning and learning in complex, partially observable domains. She works on applying these algorithms to complex problems in robotics, in healthcare, and in conversational agents. She serves on the editorial boards of the Journal of Artificial Intelligence Research and the Journal of Machine Intelligence Research, and is president-elect of the International Machine Learning Society. Last year, she was named a member of the College of New Scholars, Artists, and Scientists by the Royal Society of Canada. Ladies and gentlemen, please join me in welcoming Dr. Joelle Pineau.
Good evening. It's a pleasure to be here, and we are almost ready to start, except for my magic little clicker. Someone, I'm sure, will bring this to me very quickly. Otherwise, we'll be staring at this screen for a while. Thank you so much. Wonderful. It's a pleasure to be here. We've all heard about AI over the last year. It's been a very exciting year for people in the research community. Part of what I'm here to do today is to perhaps share some of that excitement with you more broadly, and also to demystify some of the aspects of what we actually do in this area. We're not that far away from the day where cars are going to be driving themselves. It seems like it's maybe going to be tomorrow. I assure you we have a few more years before we get there, but it's not progress that happens overnight. This is really the result of several years of work in this area. When I was doing my PhD studies in the late 1990s, I moved to Pittsburgh to attend Carnegie Mellon University, and there were folks working on developing self-driving cars. We could actually go down to a basement building, Building D it was called in the days, and when you went there, you saw some great big vehicles. One of them was reputed to have driven from one coast, from the East Coast to the West Coast, autonomously. This was 1990s. When you asked a few more questions of the engineers, what you were told, well, you know, it drove from one coast to the other about 95% of the time. That seems pretty good, right? And then you ask, which 95% of the time? Oh, the part where it was on the highway, the part where it didn't have to switch lanes, and it just followed the white line on the right, right? So we had some work to do. Between that time and now, there's been tremendous progress. A lot of that progress is in machine learning. A lot of that progress is in computer vision and our ability to understand the world. The progress is not just in autonomous driving. We're seeing it also in our interactions and our new ways of communicating, in our social interactions. It's not so unusual anymore these days to speak to a bot. Some of you may have had lovely conversations with Siri, with Echo, sometimes a little bit frustrating. They tend to have very short memory, these devices. We don't know why, because there's a big hard drive in the machine. Still, the interaction is changing. One thing that's also changing is really our interaction with all of the digital world. In many ways, all of our interaction through this digital world are mediated by AI. What information we receive, the context in which it's presented, the order in which we receive the information is decided by AI algorithms. The information that we project that is shared with the world is also mediated by AI algorithms. And so that technology has already started to impact our lives. It's not always in visible forms through cars, through assistance, but it is there in many cases. When looking at a time of big change, it's interesting to sometimes look for analogies in our past. And perhaps one relevant analogy in this case is the Great Industrial Revolution. In that case, what we observed is a period of transition where machines were suddenly able to take on tasks, mechanical, physical tasks, where human had been doing the work, now machines were doing the work. And what we're seeing with the AI revolution is that in this case, it's the cognitive parts of our contribution, our ability to think, to understand complex information, which is being taken on by the machine. And suddenly we have computer algorithms that can process information, that can plan, that can conceive of how to incorporate knowledge and do so in a way that essentially produces behavior we would associate with human intelligence. We're calling it a revolution because the impact of this new artificial cognitive technology is really showing up in many different sectors of our economies and of our societies. Let me specify a little bit more clearly what I mean by artificial intelligence. It's a collection of abilities to essentially think. And so that means modules for planning, modules for understanding natural language, understanding images, of course, trying to figure out how to learn from that information. Also the ability to actually model the world, to make predictions about the world, to search through vast amount of information. In contrast to human intelligence, our machine version right now works in silos. So we have algorithms that can do planning, algorithms that can understand images, and different algorithms that can understand images. We're still really struggling with developing machines that can cross the boundaries between these tasks. And so where we can build an algorithm that will be able to translate text from English into French, and we can build a different algorithm that'll be able to play poker. We can probably build another algorithm that can distinguish between a recording of Glenn Gould and a recording of Gordon Downey. It's difficult to build one machine that can do all of these things in an integrated way. In many ways, this is one of the challenges that lay ahead when we want to build better artificial intelligence, is to figure out what is the neural glue that we will need to make all of these abilities work in a very seamless way, something that nature has achieved beautifully. We're still struggling to get into our machines. The field of AI as a science goes back to the 1950s, and there's been a radical shift in many ways in how AI is implemented in the machines over the last few years. In the early 1950s, we had luminaries, individuals like Alan Turing, Claude Shannon, who were developing early versions of computers. And while they were building our very computers, they were already thinking of how to use these machines to behave in an intelligent way. Alan Turing was one of the first to imagine computers that could have a conversation, carry out a conversation with a human. Claude Shannon was busy building computer programs to play chess, this late 1950s, early 1960s. The approach to AI and the approach that persisted all the way through the 80s and early 90s was really an approach that was based on a programmatic philosophy of AI. In that case, we would be writing bodies of instructions, precise instructions in a machine-understandable language to tell the machine how to synthesize information and how to make good decisions. And what has changed in more recent years is really an approach that we could call a show-and-tell approach to training machines, essentially showing examples of how we make decisions and letting the machine draw its conclusions about how to perform certain tasks. So if we think of a task of analyzing, for example, images, brain images, to do segmentation of tumors in these images, it's difficult to write out a very precise set of instructions for how to detect a tumor in an image. One would probably have to give different instructions for all different brains, for different patients, different images. Even humans are trained not in a programmatic way, but really with a show and tell, by examples, by looking at many examples. And so the current AI paradigm, the one that is really kind of sweeping us off in this revolution, is one that is based on learning, on showing machine examples of how it's done and distilling that knowledge. A few breakthroughs that are really worth mentioning. Computer vision. We have really changed our ability to understand images, and one of the reasons we are now much closer to having cars that drive not only on highways but also in cities is because of these breakthroughs. Our ability to understand pedestrians, vehicles, bicycles, traffic signs, traffic lights, and so on. Once you can understand that complex information, you can actually have much more robust behavior in the world. And so in terms of image computer vision, the breakthrough was in some ways achieved by the availability of data. A group of people got together, produced a beautiful benchmark data set called ImageNet. That data set contained 1 million images, much bigger than any other data set available before. Not only were there 1 million images, these images had been annotated. So someone had gone and indicated in the image a little box around each of the key objects and had put a word to say, this is a dog, and this is a bird, and this is a car. And through this data set, we could train our machines to pick out 1,000 and more different types of objects. In 2012, we started seeing algorithms based on machine learning that were starting to exceed previous approaches based on more classical analysis of images. Around 2015, our algorithms were actually exceeding human-level performance. So the algorithm can predict more accurately what objects were in an image. A lot of that power came actually from the fact that the image could distinguish, the computer could distinguish between about 125 different categories of dogs and many dozens different categories of flowers, which most humans probably don't care to learn. When we look under the hood of these machines, what is happening in terms of the technology, their algorithms, computer program telling us how to learn. In many ways, the algorithms that were behind these breakthroughs had many elements that had been known for 15, 20 years. What really changed our ability to solve the problem was the availability of the very large data set and the availability of computing platforms, GPU platforms, to compute the algorithms. Speech recognition, similar process where we saw quick improvement, in particular around 2010, 2012, and so on. Our ability to understand natural language from audio to written speech improved drastically. These are two different domains, understanding images, understanding speech, and yet in some ways, this deep learning technology is the engine that drives these progresses. It's been applied to many other types of data also. And here in Canada, we've been really lucky to be at the forefront of this revolution. We've been sitting in the front seat watching it happen. Because we've had some of the leading researchers, Alan mentioned them in his introduction, who've been really leading this way. Jeff Hinton, Jan LeCun, Yashua Bengio, and of course, the great population of grad students that they've trained over the years. All of them have been training many, many grad students who have now moved on to join university and industry labs around the world carrying out this work. Let's look a little bit deeper under the hood and try to understand what's going on in this case. One analogy that is quite interesting to look at is the parallel between biological neurons and what we're calling artificial neurons, because this deep learning is really a way to adapt some of these intuitions. So in a biological neuron, you can think of a biological neurons, and my biology friends in the room will forgive me if I do this in a very crude way. Essentially, you can think of it as a unit of computation. It's a unit in the brain which receives information. There's some dendrites at one end of the neuron that receive messages from other neurons. There's some operation that gets computed inside the neuron, the neurochemical level, and then the neuron decides whether to send out a message or not. And if it decides to send out a message, there's essentially an electrical message passed along the axon that gets sent around to many other neurons. And so this notion that information gets in, something gets decided, and in some cases information goes out is very similar to what's going on in our artificial neurons. In that case, the neuron is actually a line of code or a unit in memory in the computer that receives information from other pieces of the memory in the computer or information from sensors in the case of a robot. Information is computed at the level of the neuron and gets passed on to other neurons. And things get really interesting when we combine many of these neurons together. We're not very good at building very complex, intricate ways to combine this. We usually layer out our neurons in a set of different layers. It's quite useful just from a mathematical point of view in that we have to, in the end of the day, represent this in the memory of a computer. So we have vectors and arrays, and information gets plugged into there. The connections between the neurons essentially are the process through which we acquire learning. And so by strengthening connections between certain neurons, we can actually strengthen certain predictions. So when we talk about training a machine learning algorithm, what we really mean is figuring out what is the right set of weights on these connections, how strong or how weak to make these connections, in a way that once the message gets passed through all of the layers of neurons, we have a prediction at the end that matches what the label should be. So if you think of trying to do image classification in this case, I would take an image. On the input side, each of the pixels in the image would be associated with a separate neurons. And through each of the layers of the neural network, we're computing more and more abstract version of the information, from lines and color patches to patterns, to the end predicting whether it's a dog or a cat that's in the neural network. Things get particularly interesting when you start to stack many, many layers of these neurons together, dozens of layers of these neurons. This is one of the network, the Google Net, that was doing very well a few years ago in terms of the ImageNet challenge. It has on the order of 600,000 neurons. There's about 6 million parameters to train over here. So you can imagine the amount of data you need to see to get good weight configurations on these 6 million parameters. The progress we're doing is not limited to just images or just speech. There's really interesting work being done at the intersection of vision and language. This is a case that deals with the problem of image captioning. So in this case, the neural network receives an image. We present an image, and the goal of the machine is to produce not just one word, right? Not just pizza, but a whole sentence, right? 2 pizzas sitting on top of a stovetop oven, right? Generating that sentence, all of the words, in a way that is consistent with what's shown in the image, but also consistent with the rules of grammar. In this case, in the English language, though we can do that in several other languages also. The second image, the label that was generated, a group of young people playing a game of Frisbee. Quite remarkable, something that a few years ago we really couldn't think of doing. The machines are not perfect, right? We have a great set of bloopers. On the left here, obviously, a refrigerator filled with lots of food and drinks, right? That your fridge looks like? I don't think so. On the other side, a yellow school bus parked in a parking lot. Not quite. It's quite likely that in our data set, most of the images that featured transportation and something big in yellow were a yellow school bus. Probably not a lot of images of cars like that in our training data set. And so you start to see that in many cases our algorithms are making mistakes when they haven't been exposed to the right kind of data. One technique that we have been looking at to improve in cases where our machines are not doing as well as we want is by letting the machine on its own improve its ability. And so there's a branch of machine learning called reinforcement learning that pursues the development of algorithms for that case. In the case of reinforcement learning, the strategy is a little bit different, right? Deep learning typically is a supervised learning approach. I will show you an image. I will tell you there's a dog in that image. In reinforcement learning, the machine gets to apply a little bit more trial and error. It's not that different from how animals, pets learn or how children may learn, right? They try different behaviors, and sometimes these behaviors result in a good reward. The animal may find food. The children may receive positive reinforcement from their parents. The agent learns through trial and error to exhibit behaviors that are consistent with getting a lot of reward. And so we're essentially building algorithms to train our machines in that way. The advantage of this is that we don't then need to be very systematic about providing the teaching examples. The machine can try out different behaviors and learn which behaviors learn to finding the cheese in the maze and which behavior lead to just finding yourself in a corner. Perhaps the greatest success of reinforcement learning over the last few years is the AlphaGo system produced by DeepMind was able to essentially learn how to play the game of Go It was spectacular success. Many people in the AI community thought we were still a decade away from being able to crack this game. Very difficult game for many reasons. And yet 2016, we had a system built with a combination of deep learning. In the deep learning piece of the system, they leveraged several games from experts, millions of games from expert Go player, and they essentially got the machine to imitate what the Go player was doing. So that's a supervised learning approach. And then when it got to a certain level of performance, they told the machine to go ahead and play against itself. And that's what allowed the machine to get to the next level of performance, beat the human champion at this very difficult game. The results were published in a Nature paper and were really quite interesting from the community. Perhaps what's interesting to note is if you look closely at who were the authors on this Nature paper, at least 5 of them were actually trained in Canada, in Montreal, in Toronto, and Edmonton. They did their graduate studies here and are now working at DeepMind, working on this project. Last week, another phenomenal result from the same team. In this case, the ability to master the game of Go without any human knowledge. So in this case, they forgo looking at any previous games by expert, and the machine, through self-play, starting from scratch, complete inability to play, all the way to a level beyond any human player, completely trained by self-play. So really interesting result still coming out. For those of you who may be motivated for higher impact applications than the game of Go, there is so much potential for using both supervised learning and reinforcement learning, in particular in the field of healthcare. And I will finish by spending just a few minutes talking about one of the projects that's been carried out at McGill, in part by students in my own lab. We've been looking for several years at how to improve our ability to treat individuals with epilepsy. Epilepsy is one of the most prevalent neurological diseases. In many cases, patients can be treated by pharmacological drug treatment. In some cases, surgery is also a good solution. But for some patients, in particular, when the seizures are spread out across several sections of the brain, it's hard to go in there and do resection surgery without impacting cognitive abilities. And so we've been looking at therapies, in particular neurostimulation therapy, where a device applies electrical stimulation in the brain in real time in an attempt to disrupt the incidence of seizures. The technology has been developed over a few years, but there's really interesting question in terms of how do we optimize the parameter of the stimulation such that we can improve our ability to disrupt seizures. This is an example of a seizure as seen in the EEG signal. So in this case, the information we get from the world is in the form of this EEG, sampled at high frequency from the brains. Often we have several sensors in parallel electrodes recording this. In this case, there's a very nice deflection in the middle, which is the seizure that we're considering. So what we want is essentially to be able to disrupt this seizure sufficiently. And the idea of neurostimulation, the theory behind neurostimulation, is that epilepsy occurs when several of the neurons in the brain are essentially recruited to all fire in a synchronous manner. So they all start firing at the same time, which causes this big disruption. And after a while, the neurochemicals are depleted and they can't fire anymore. And then there's a period post-seizure that happens. And so by applying neurostimulation, every time electrical stimulation is applied, that forces some of the neurons nearby to fire, which then forces some of the other neurons to fire. So you're essentially disrupting the ability for the brain to hypersynchronize, and therefore seizures can't happen. And so what we're really interested in doing is figuring out how can we optimize the parameter of that neurostimulation strategy and do it in a way that we can improve the outcomes for individuals. Epilepsy is a highly variable disease. The types of seizures, how they occur, how they manifest, changes a lot from one person to another. So there's not really a sense that one set of parameters in the device is going to be helpful for many individuals. There's really an opportunity there to learn through trial and error what might be the right strategy, the right configuration of parameters to maximally benefit a particular individual. And so we started a project a few years ago in collaboration with researchers at the Montreal Neurological Institute to design a better AI-driven control algorithm for neurostimulation devices, where the input was this multi-channel EEG signal, and the output was actually a schedule on the stimulation, something that would tell the stimulating electrode when to send a signal and when to hold back. The idea was that we would attempt to minimize the incidence of seizures but also to simultaneously minimize the amount of stimulation that we deliver, such that we can actually preserve healthy tissue, preserve battery on the device. And so we used reinforcement learning to optimize this strategy, and we were able to show that we come up with a policy that's highly diverse. What you're seeing, the little bars down there, right, that's the policy that was discovered by the AI agent. What you'll see is that in some phases, there's increased amount of stimulation that happens just at the moment where there seems like there might be seizure onset. There's a greater incidence of these spikes, which we call these interictal events. And later on in the process, this policy spaces out, so we can actually space out much more the incidence of stimulation because we know that the brain is not in an immediate risk of seizing at that point. These are experiments we conducted with animal models of epilepsy. We haven't yet moved on to human experiments. As you can imagine, having an AI system disrupt a neural system is something that is not without risk, and so we have to be very careful in our experimentation, but animal models provide a really great way to be able to acquire data and test out some of these ideas. This is but one example of really a broader movement towards looking at AI strategies for optimizing treatment, and in particular, optimizing personal treatment. I'm particularly interested in seeing how well we can do for all of these diseases where you need a sequence of interventions. There's some disease where it's easier to think of a single intervention, but there's many cases, I've listed a few there, where we have collaborations between AI researchers and medical researchers to try to improve the outcomes by optimizing the discovery as well as the personalization of the treatment strategy. Let me close with a few final remarks. First of all, there's a few ingredients in my mind to have a successful AI revolution. One of them that we talk a lot about is the incidence of data, right? Lots of data. Lots of data is often fabulous. We don't always have the privilege of lots of data. The work that we did with epilepsy in particular, we had data from about a dozen animals. It's not a lot of data. It may look like a lot. The file may be big on the computer because we're recording from multiple channels, but having just a dozen animals with epilepsy, I assure you, is a very small sample. And so we have to learn as efficiently as we can from the data that is available. In some cases, we need very high-performance computing infrastructure to help us process through the data. When we're looking at robotics, autonomous driving, we have data coming in from multiple cameras. We have data coming from these three-dimensional point clouds. It generates a ton of data. So we have to be able to process through that quickly in real time. Of course, we need a team of talented computer scientists, data scientists, machine learning experts. One of the big challenges for our universities in the next few years is to train and produce the talent at the speed that everyone is hoping we will, and to be able to help our industry, our public institutions, have people who have these kinds of qualification, help them in this transition time. In many cases, we also need to have good domain-specific knowledge. So when I look at applying machine learning techniques to improve the treatment of healthcare, I can't go in there on my own with my machine learning toolkit and hope to crack a problem, such as how do we improve the treatment for epilepsy. There has to be a close collaboration with people who understand the disease, the dynamics, people who work with the patients, people who know how the healthcare system works, and we can think of how we will deploy the strategies in a way that's effective in the ecosystem. And finally, of course, we need to have more efficient learning algorithms, architectures. A lot of the research we do in our labs is really on this fifth point below. But all of the ingredients have to be aligned, I think, for us to be able to make progress. There's been a lot of noise about IT companies competing for AI talent. This is just but a very small sample of companies where we have seen a lot of AI activities in the recent years. In many cases, right, they're opening the field. But as we progress, really what we need is to figure out how we can have AI talent, but also AI readiness across many, many different sectors of our economy and our societies. And so this is one of the challenges that I think is ahead for us in Canada. Fortunately, I think one of the reasons we have been able to lead the way in this is really because we have a pan-Canadian strategy on this. There's talent from coast to coast. The bigger centers are in Toronto, Montreal, Edmonton, but there's several excellent researchers and training programs in many other cities, in Vancouver, in Waterloo, in Quebec City, and across the board. And so that next generation of students is soon going to be coming out of our universities, and we hope are going to help us in the future doing this. And let me close with just saying that I look forward to the discussion with the Massey Fellows. Thank you.
I'm now going to invite 3 junior fellows of Massey, graduate students, to join me here on the stage so that they can put some questions to our guest of honor. Sitting next to Joelle is Joanna Pokorny, a PhD candidate in her 5th year at the Department of Anthropology, University of Toronto, and a junior fellow at Massey College. In her dissertation project, which is situated at the intersection of anthropology and science studies, Joanna ethnographically studies the laboratory life of a group of neuroscientists who take up recent ideas of neuroplasticity, resting state research, neuroimaging, and computational neuroscience techniques to studying the living and dynamic brain. And sitting next to Joanna is Shane Saunderson. No, Shane Saunderson is at the far end, I'm sorry. He is a first-year, non-resident junior fellow at Massey College and is currently pursuing a PhD in robotics at the University of Toronto. He holds an MBA in Technology and Innovation from the Ted Rogers School of Management at Ryerson University and a Bachelor in English from McGill University in Montreal. And sitting between those 2 junior fellows is Sasha Milish, first-year resident junior fellow, doctoral student in the Computer Science Department. Her primary research area is computational linguistics, the study of natural human language from the viewpoint of computer science. In particular, she's interested in what computational models of human language say about the human mind. I will leave the stage now because junior fellows at Massey College do not need any moderation. In fact, they resist it as a matter of principle, which I think is a good thing. Over to you, colleagues.
Well, I'll begin. Thank you so much, Joelle, for a wonderful talk. I want to get right into the discussion by focusing on some of the socioeconomic impacts of AI, so specifically the rapid economic disruption it will introduce, such as job displacement, and perhaps the attendant increasing wealth disparities that may come with this. So being familiar with the innovation in AI development, what sorts of policy and/or preparation would you recommend we take to deal with these socioeconomic impacts?
I'm not a policy expert, right? I write computer algorithms, and it's hard to write a computer algorithm to produce good policy, I can assure you. One thing I can say is, you know, there's a lot of prediction now about trying to just figure out, in particular, which sectors of our industry are most likely to change, and trying to figure out in what way to prepare, in a sense, the next generation for that change. Some of the changes that we worry about on the onset, right, self-driving car being one of them. There's a huge number of people who make a living driving, trucks, cars, and so on. It's interesting to talk to people on the industry side, in particular for the trucking industry. One thing we're hearing from leaders in that is that it's very difficult for them to recruit new people to that particular job. It turns out that driving large trucks coast to coast, long hours, is not a really attractive job for many people. And so even industry leaders are looking forward to having more automation to relieve some of the pressure. It's not the same in all sectors. When we talk to people in radiology and we evoke the possibility that radiologists will perhaps not be so useful, in that case it's a little bit of a shock because it's people who have many, many years of studies And so it's a little bit difficult to help them prepare or for them to accept that reality. I would say just looking at the spectrum of occupations, right? One thing that stands out is cases where jobs where the type of information that has to be processed is relatively uniform, right? One reason it's easier to think that we may have machines replacing radiologists than emergency room physician is because in one case it's very uniform information, so it's easier to train a machine for. Whenever someone has to process very complex information and also perform a really wide variety of actions, it's a lot harder to think of machines taking on these roles. But that's a little bit far away from policy, I realize. But at least rule of thumb of seeing where we're going to see the most disruption. Going back to the maybe a little bit closer to your question, right? This, how do we prepare for this? In a way, I think human society is incredibly adaptable. I had a colleague who gave a presentation on this recently and quoted the following statistics. He said at the beginning of the 20th century, there was about 40% of Americans who were engaged in agriculture. And at the end of the century, it was about 4% of Americans who were working in agriculture, and yet unemployment rate was lower. And also during that century, we saw the massive movement of women into the workforce. And so I think the jobs that will be available for our children are going to be completely different than the jobs that were available when I went to university and perhaps when you went to university. But I think that there will be very interesting problems to solve and things to do.
Do you have any recommendations to us as young scholars? I know you mentioned you prepare your daughter a little bit. So do you have any recommendations for young people as to how they should prepare?
I try not to intervene too much in her long-term plan and give her space, you know. But yes, I think, you know, acquiring a really large diversity of skills is always useful, right? Something to think about. Mathematics and science are definitely going to be very useful in many ways. I think in particular we have a big challenge in terms of how to incorporate more computing into our curriculum at the lower level. I know a lot of the people looking at the curriculum for the K-12 are really looking at how can we introduce children to computing, programming earlier, and how to do it in an age-appropriate way. And so I expect there's going to be a lot of movement in that respect over the next few years.
Quick follow-up, if I can jump in.
Sure.
Two things I want to pick on and kind of question. You mentioned at the end, you know, how are we incorporating more technical perspectives and coding into different curriculums. You also mentioned at the start, you know, in your humility of, well, I'm not necessarily one to comment on policy. To what degree do we need to be worrying about technical practitioners, coders, engineers, not necessarily having a broad enough perspective on what they're doing and some of the ethical implications of AI?
It's very interesting. Right now, because the technology gets better, it becomes much more important to have these conversations across different fields and boundaries. And I think the issue that you point out is definitely there, right? As much as we have people on the one side who are building policies, looking at the ethical implications, who may not have had the opportunity to have the more technical computing training. On the other side, we also have people who have been trained in a very narrow scientific way and may not have as much broader culture in terms of the sociological impacts, policy impacts, economics, and so on. And so we have a gap, which usually means that when we have these conversations, it takes us a while to find a common language. I'm really hopeful that the next generation will not have as much of a gap, that we will have an ability to, you know, go back to Renaissance type of training where people were really exposed to a much broader spectrum of ideas.
Make more polymaths. Yeah.
Thank you for such an insightful answer. I have a question that kind of goes in a different direction. It seems like current AI algorithms are largely inspired by the human brain, and I'm wondering, do you see this inspiring or guiding research, AI research, for the foreseeable future? And I suppose another way of saying this is the human brain the gold standard for AI research, or could it possibly go in a different direction?
Yeah. I think you'll get different answers depending who you ask. And since I have the stage today, I'll give you my version, but take it with a grain of salt. The human brain is a beautiful machine, but it's also one that we understand very, very poorly, right? In some sense, people worry about not understanding what's going on when a machine makes a decision. But I can tell you, I can trace that decision in a machine much better than I can trace it in a human right now. And so the human brain is great inspiration, but we don't understand everything that's going on in there. The other aspect is that the human brain and the machine have different materials, different biology, right? And so there's some constraints, physical constraints, that are associated with those differences. And so some things that the brain can do, we cannot do in the machines because these physical constraints are different. And I should also say, right, we talk about reinforcement learning, which has nice parallel with psychology. We talk about neural networks, which have nice parallels with neurons. But there's a whole lot of other things going on under the hood in terms of training a neural network. There's a ton of optimization that's built in. These techniques from optimization come to us not from biology inspiration. They really come from a really fundamental understanding of mathematics and how to optimize functions. And so there's a merging of these ideas, and I think the human brain analogy speaks to people, and it's easy to both for the scientists to draw inspiration and for us to communicate across boundaries of field, but it's only a piece of the story of how we really build these algorithms.
Thank you.
My turn. I guess the engineer / businessman in me wants to get a little bit applied, so I'll ask you a double-pronged question. What's been the most interesting or your favorite application that you've seen of AI so far, and what are you most excited for that's on the horizon?
The most exciting that I've seen?
Yeah,
I can tell you one of the things that I've been most excited to work on, really, is this epilepsy project that I talked about. That's why we've done many projects over the years, but this is one that I've been most excited about just because it's been so hard to do. There's really a beautiful problem, right? There's people who live with epilepsy, which I could go on for a long time, but it's a disease that really impacts people's lives, their ability to carry out normal activities. And yet we have this really interesting new technology solution. We don't have a lot of data to solve the problem. We have these animal models that are really different from the humans, but they're kind of the best we have to get the data. And so, but this kind of problem, there are so many of them across the way. And one thing that's wonderful about working in AI right now is that essentially the doors of all these other fields are open to you. I never studied, I haven't even studied biology in high school. This is embarrassing to admit on such a big stage, but right, I didn't take high school biology. And yet, because I know something about data science and about mathematics and algorithms, I get to work with some of the world's best neuroscientists trying to solve these problems. And we kind of come at it from our different limited point of views. And so that type of interdisciplinary project is so exciting. There's so many cool ones to do.
Yeah, great.
Okay, so you've mentioned data a lot right there. There were challenges in there, but data and algorithms have come up multiple times. What can algorithms and data not do? What can they not do today that you think they might do in the near future? And is there something maybe they might never be able to do?
I would say, there's usually you have to ask the right question of your data. So it's a question, it's a little bit of a dance between the data and the algorithm. And if you take the data and you pair it with the wrong algorithm, then you're not going to get a very interesting answer. So one of our challenges as we do the more applied side of this work is really to look at the data, become familiar with the data, try to understand, what does it smell like? What is its color? What does it sound like? Really try to get the characteristics of that data, and then to pair up the best algorithms that we have. And in some case, we don't have the right fit, right? It's just not the right shoe for that foot. And we have to go and make a new shoe. But really, a lot of what we do is trying to do that. And so if we find cases where we don't have a good set of algorithms to match with new data, then this is often when we get more creative, and we're going to go and create new algorithms to fit that data.
Ooh, so it's an exciting place.
How often do you have to invent a new algorithm? Are you usually just picking things out of your toolbox, or how often do you have to get creative?
Like every week.
Oh.
I'm not saying I invent a great
Right,
new
right.
algorithms every week, but yeah, every week I have a fantastic group of grad students. I have about 15 grad students or so at McGill who are so creative. And it's often the case that, you know, we pick problems that are hard enough that we don't have the right algorithms to solve them. And that's when things get interesting. Sometimes when we start a new project, we don't know yet, right? I'll have a first conversation, and I had a colleague at McGill we had a meeting a year or two ago. He had wonderful data tracking primates in Zimbabwe, and he had like the tracking data from them over several years. And he was like, what can I predict with this data? And honestly, we didn't know. We started playing with the data. We tried to build predictive models. So if you see where the primate has been over several days, can you predict where they're going to go next? And it turns out the best algorithms we had were not doing a very good job. And so then we build a new set of algorithms for doing that our new model for time series prediction. We applied it for these particular primates, but now the algorithm's out. We published it, and then people can use it for whatever other types of data that they might have. So I would say every week we work on trying to create new algorithms. Some of them don't pan out. Many of them don't pan out. Once in a while we hit on a good idea.
Joelle, what do you think is the largest misconception the general public has about AI? Or the current state of AI?
One of the misconceptions, I think, is the fact that AI is this black box that's making decisions, right? Information goes in, black box does something to the information, and out pops a decision. And this notion that we can never understand what's going on in the black box, right? And this goes back, I think, to a comment I made earlier. I think in many ways we know what's going on in the black box, right? I have a neural network. It may have 600,000 neurons. If I present the same image, I can trace very precisely where I'd predicted that this was actually an image of a fish. I can trace it. The difficulty is it's not a simple story. And so once I've traced it all, I can't necessarily go and explain to you in 20 words or less why it decided that it was a fish. Humans are much better at doing that. Humans are much better at saying, well, here was the context, and I made this decision, and here's why I made this decision, right? Humans are good at coming up with that short answer. Now, what's interesting is that in many cases, it's not clear that the human answer, the reason humans are giving, is actually the reason they made that decision. And so we can't go back in their brain and trace what was the sequence of neurons that fired very precisely to go from seeing that information, right? You're driving along, you see something, and you decide to veer to the right or hit the brakes. The human may bring a narration to explain it, but we don't have a clue what's going on. And so people have this notion that, oh, humans are so understandable and explainable, and machines are these black boxes where we know nothing about what happens. I think it's the other way around. It's just that humans are really good at building a narration, and machines are not so good at building a narration yet.
So what happens when we make the machines that can build the narration as well? Is that a good thing or a bad thing?
Well, I think that's a good thing. If anything, it's a good thing because it establishes a richer dialogue between the machine and the human. And the reason we need this richer dialogue is because as we move forward, right, we talked about some of the fact that machines are going to become more prevalent in the workforce. As we move along, humans and machines are going to work together. It's not going to be a case of suddenly, right, all the machines move into the workforce, we close the doors, and the humans go off and we play golf for the next several years. Right, for a long time, there's going to be a partnership. The machines are going to make predictions. The humans are going to look at it. They'll take some of that, and then they'll change some of the other ones. And so we need to have a language for explaining each other's decision. Humans need to have a language for expressing what they think to the machines. We have coding for that. Machine needs a language to express to humans what they're doing and why.
Okay. On the topic of coding and data, I want to talk a little bit about a bias in data. So one of the things that's often raised with training algorithms through providing it with mass amounts of data is that the data is inherently human, which means it could be inherently biased or flawed. And a lot of people even call out, potential, isms, racism, sexism, those kinds of biases that could work their way into data. But I actually want to talk more just about capability. What are the risks of introducing the bias of simply the fact that our data is human in nature, and that means that we can only ever get something that we produce that is human and never better?
Right. There's no doubt that human bring in knowledge, right? And human bring in bias by selecting the data in some cases. Depending on what's the data set that you've selected, your machine is going to train from that data. That bias can be very powerful, right? There's a principle in machine learning which we call inductive bias. And this is essential to training. And that is essentially, if I can try to simplify, inductive bias is essentially the knowledge that we put in to constrain the problem, to make it feasible to learn something. So, for example, when we do image classification, it's deciding what are the set of classes, the types of object, right? Are we going to look at 5 objects or 5 million objects? Deciding what's the set of objects that matter, that we want to be able to predict, right? This inductive bias is very powerful because it allows us to narrow in on learning the things that we think are important. The other side of this is bias, plain and simple, which is it's limiting the ability for the machine to learn anything. And so there's the good side and there's the bad side of this. And we have to be very conscious when we design our system. We have to be conscious to pick a good inductive bias and also to check our biases in terms of what data we use. There's a line of research, people are looking very actively at building models where we can actually detect or even revert bias in our predictions. So try to make decisions that don't exhibit certain preferences for different types. And we're achieving some measure of success for doing that. I would say the caveat is that we have to be aware of our biases to do that. So to be able to balance away from a particular bias, we have to be on the watch for it and be able to sort of name it to compensate for it. And so one of the ways we do it is by overrepresenting underrepresented types of data. And so rather than take the whole data as it is uniformly, we're going to say, well, we want to be better at this type of behavior, so we're going to increase the weight of that data, reduce the weight of that data. And so there's sort of algorithmic things we can do, but then they require us to put a little bit of knowledge. The completely unconscious bias is very hard to prevent.
Okay. And is there any way we can break free of not even bias, but just limitation and start talking? I mean, now we're kind of getting into the realm of superintelligence and things like that, but how do we actually go beyond not just human bias, but human capacity?
Yeah, so that was the other part of your question. In many ways, this is what reinforcement learning brings to the table, right? Supervised learning says, I'll show you an example, and a human will put a label on it, and then the machine will learn these pairings. In reinforcement learning, we have the ability for the machine to learn from itself, to explore different strategies, and then to see these rewards. There's still the notion of a reward. So when they built the system to play Go, it didn't have any games from experts, but someone still wrote down in that computer program the fact that winning the game was good and losing the game was bad. Yeah, and if we had written it the other way around, we would have gotten a beautiful Go losing machine. And so that piece still has to be written in, but in reinforcement learning, you'll write a lot less. It doesn't mean that it's not hard. And one of the problems we're facing specifically with reinforcement learning, it's a problem sometimes we call the value alignment problem. It's easy when you're building an agent to play chess or to play Go to just say winning is good, losing is bad. It's a lot harder when you build a robot to drive in the street to figure out what is the right reward function to specify for our agent. And that's when we get into very difficult, more ethical issues of figuring out how to trade off different choices and how to write out the reward function, the cost function for these different choices.
Yeah. Okay.
So following up on some of these challenges, there's a lot of sort of dystopic visions of technological advancement. There's a lot of fear and anxiety, especially in the press, around AI development. Perhaps from a more agnostic perspective, technological development is neither always perilous nor promissory. So from your point of view, as an expert in AI, what are the sorts of things that sort of make you perilous about this? What are challenges, complications, things that you see as problems ahead?
There's a lot of challenges ahead. We've touched on a few. One of the challenges we perhaps didn't touch on is issues of privacy and security with respect to the data. There's a lot of data that is being collected from people's behaviors. That data is stored, shared in multiple different ways. Thinking of how do we preserve the integrity of the data, especially when we get into medical data, is very important to do. So we have to figure out the right way to do that. There's something really subtle that creeps in when you're doing machine learning, which is, I mean, everyone agrees that, you know, the raw data should be preserved and we should be careful about who has access to it. Now you take this raw data and you train a machine learning algorithm. That machine learning algorithm captures something about the data. That's how it makes the decision. But people don't necessarily have any qualms about sharing that algorithm and distributing the algorithms, and the weights that are associated with that contain a piece of that data. And so understanding carefully what it is that we're sharing when we share data-driven system is a really interesting problem that has both sort of technical aspects as well as ethical aspects. Another one that I spend some time thinking about is how do we make sure that we have a diverse representation in terms of the people building the technology, building AI? As a woman in tech, you know, this has been a familiar theme throughout my career. But there's really a sense that as researchers, a lot of our job is picking the right questions to ask. And when we pick the question, we're directing the research agenda. And so if we have a very narrow segment of our population asking all the questions and then building all the technology, then we're going to have a pretty possibly narrow set of technology, and it's a challenge to get a lot more contributions from a much more diverse segment of our population.
Do you have ways of maybe thinking about how to bring in those diverse perspectives, or ways in which you engage in it in your lab or at the university?
There's a lot of initiatives underway, I have to say. We had a beautiful summer program at McGill last summer called AI for Good, which brought together about 25 young women at the end of their engineering or computer science degree to do advanced training in AI as well as practical projects, and they had industry mentorship or so on. It's a pretty small program. It's 25 of them. It's the kind of thing we would want to have, 5,000 people do. But it takes a lot of energy to push these initiatives through. And this is just one example. There's these kinds of initiatives everywhere. We're still, I think, not super good about measuring the impact of these things, trying to figure out how we can have the most impact. As we prepare to introduce coding into a lot of the elementary school curriculum, thinking of a way to introduce coding that is appropriate, that it will appeal to a large segment of the children is really important. And it's not something that's necessarily easy.
You've touched on this in several of your answers, but I feel like I might as well ask explicitly. What do you think right now is the greatest bottleneck to AI research or AI development?
On the more research side or on the more deployment side?
Either way.
I think on the deployment side, right, the thing we keep on hearing is really the bottleneck in terms of talent, the ability to train more people in this relatively quickly. I would say all the different sectors, right, companies come to see me and they want to hire my students much, much faster than I can help them develop. And so we have this challenge in terms of training the next generation of students.
What do you feel, how do you feel it's most appropriate to train? Like, do you feel like a 5-year PhD graduate program is the ideal way to train an AI researcher? Are there quicker ways, or is that something?
I don't know yet. I don't have the answer to that one. I think that the spectrum of opportunities is so wide that there's an opportunity to do better at all levels, quite honestly. Yeah, I don't know what you guys think. You guys are like all early or later stage of a PhD.
If they want to let us out sooner, that's fine.
I honestly think it's a shame that students don't learn computer science the way they learn chemistry, biology, and physics, which I think things are probably going to change. I know nothing about education, but I feel like if people are thinking, they're going to try to put in computer science programs into public schools.
Yeah, I think we're 10 years late on that. I wish we had started doing that 10 years ago, but better now immediately than in 10 years. Yeah.
Okay, I think we're all done on time, so just on behalf of the three of us and the entire community at Massey, thank you again so much for the talk.
My pleasure, thank you.
Hugh, I think you and I have the best jobs, not only in Canada, but in the world. You get to interact with 150 fabulous junior fellows, like the three that we've just heard from. And I get to interact with 350 CIFAR fellows of the kind like we just heard from Joelle. Joelle, I want to thank you first for just an amazing job of your enthusiasm, your ability to explain really complex concepts and ideas and algorithms to a very diverse audience is just amazing to watch. It's a great performance. I'm not sure it's the same as a Glenn Gould Brandenburg Concerto piece, but it's pretty good. So thank you very, very much for your time and for just doing a wonderful job for all of us here. Thank you. And Sasha, Johanna, and Shane, you're terrific. And every time I go to a CIFAR, a dinner at Massey with junior fellows, I leave with the same feeling I have right now, which is the world's in good hands. So thank you very much for your time. Hugh, when you and I had this conversation 3+ years ago of having a partnership to bring CIFAR fellows of the caliber of Joelle Pineau to talk about issues of the day that matter at the nexus between science and society, I certainly didn't appreciate how important and how relevant this would be. And I think it was a great partnership, and I look forward to continuing this partnership between CIFAR and Massey. So thank you very much. I'd like to thank all of you for coming. I hope you found the evening as stimulating and as informative as I have. You can continue the conversation. There'll be a reception outside afterwards with any of these four individuals, and our staff will be out there if you want to ask them more questions about CIFAR. Again, I'd like to thank Hugh for partnering with us on this great event. We have an event coming up on November the 14th. It's our annual dinner, CIFAR's annual dinner at the Omni King Edward Hotel. It is going to feature a fabulous talk by another CIFAR fellow, Michelle Lamont from Harvard University. She's co-director of CIFAR's program in Successful Societies. Michelle is Canadian. She's the president of the American Sociological Association, and she's this year's recipient of the Erasmus Prize, which will be given by the King of the Netherlands later this fall. And Michelle will be talking about addressing the recognition gap, how to make societies more inclusive. Thank you all again for your talk, for your time, and to the audience for coming this evening. And please join all of us out in the reception after this. Thank you very much.